Mathematics 1, DM015 by Mathematics Unit, KMNS. Chapter 4, Functions. Subtopics in this chapter. 4.1 Relations and Functions, 4.2 Types of Functions, 4.3 Composite Function, and 4.4 Inverse Function. We will discuss 4.4 Inverse Function. Inverse functions. At the end of this topic, students should be able to show whether a function has an inverse and find the inverse of the function by using algebraic approach or graphical approach, and compute the inverse of a function. Inverse function. What is inverse function? Definition. If f is a function that maps x to y, then the inverse function is denoted by f inverse x. By using an arrow diagram, if fx equals y, then f inverse y equals x. An inverse function of f exists only if the function is one-to-one and onto function. One-to-one and onto. They are one-to-one but not onto. For example, we have two sets of elements. X has elements A, B, C, and Y has element 1, 2, 3, 4. All element in X has image in elements of Y. But not all element in Y has object in X. Therefore, this is not onto. One-to-one and onto. How? We represent it by using arrow diagram. If we have elements of set X, A, B, C that has image in set Y, 1, 2, 3, all the elements in set X has image in set Y, and all element in set Y has object in set X. Therefore, this is one-to-one and onto. The definition of onto: for every element in codomain, there exists an element in the domain which maps to it. For example, in graph, from this graph fx equals 3x minus 4, we can see that all values of x has coordinate of y, and for all coordinate of y, it has its own coordinate x. The second graph, fx equals x cubed. This is also an example of one-to-one and onto function. How can we determine a graph of one-to-one and onto? We can use horizontal line test, a test which is used to determine a one-to-one function. If a horizontal line intersects the graph of a function more than once, then the function is not one-to-one function. And if the function is not one-to-one function, it has no inverse. As example, this graph. This is the graph of quadratic functions. When we draw a horizontal line test, we can see that there are two intersection points of the horizontal line and the graph. Therefore, this is not the graph of one-to-one function. For the second graph, a linear function. When we draw a horizontal line y equals k, there is only one intersection point with this graph. Therefore, this is the function of one-to-one. By using algebraic approach, a function fx is one-to-one if fx1 equals fx2, then x1 equals x2. Therefore, we can conclude example 1. F is one-to-one function. Determine whether fx is a one-to-one function by algebraic approach or horizontal line test. For example, function fx equals 7x plus 9. By using algebraic approach, fx1 equals fx2. fx1 means 7 x1 plus 9, and fx2 means 7 x2 plus 9. Simplifying this, we get 7x1 equals 7x2, and we get x1 equals x2. Since fx1 equals fx2 implies x1 equals x2, therefore f is one-to-one function. By using graph, we test the function by using horizontal line test. Draw the graph of fx equals 7x plus 9. We get a straight line like this, and draw any horizontal line on the graph. Any horizontal line. Let's say y equals k. We have only one intersection point of the horizontal line and the graph. Therefore, y equals k intersects the graph at one point only. F is one-to-one function. Determine whether fx is a one-to-one function by algebraic approach or horizontal line test. For the second function, fx equals 3 minus 4x squared. By using algebraic approach, fx1 equals fx2. Then fx equals 3 minus 4x squared. Therefore, we get 3 minus 4x1 squared equals 3 minus 4x2 squared. Simplifying this, we get negative 4x1 squared equals negative 4x2 squared. And we get x1 squared equals x2 squared. Since x1 squared equals x2 squared, we get x1 equals plus minus x2, which fx1 equals x2 implies x1 equals x2 or x1 equals negative x2. Therefore, this is is not one-to-one function. By sketching the graph and using horizontal line test, we sketch the graph of y equals 3 minus 4x squared. And when we draw a horizontal line test, there are two intersection points of the horizontal line and the graph. Therefore, f is not one-to-one function. Determine whether fx is a one-to-one function by algebraic approach or horizontal line test. For the function fx equals x squared minus 2x plus 3. By using algebraic approach, we have to start or begin with let fx1 equals fx2. Therefore, fx1 from the function equals x1 squared minus 2x1 plus 3. And for fx2, from the function, we get x2 squared minus 2x2 plus 3. We need to simplify this equation. We have x1 squared minus 2x1 equals x2 squared minus 2x2. What can we do? We can factorize x1 and x2. Therefore, group x1 squared and 2x2 squared together. x1 squared minus x2 squared equals to x1 minus 2x2 now. Therefore, x1 squared minus x2 squared can be factorized. Becomes x1 minus x2 times x1 plus x2. And we factorize 2 on the right hand side. We get 2 times x1 minus x2. Therefore, we can cancel x1 minus x2 on the both sides. And we have x1 plus x2 equals 2. Therefore, we didn't get x1 equals x2. We get x1 equals 2 minus x2, which is shown that this function is not one-to-one function. By using horizontal line test, what should we do is draw the graph of x squared minus 2x plus 3. This is a smile graph with a minimum point here. And we draw any horizontal line y equals k. And we can see that there are two intersection points of the graph and the line. Therefore, y equals k intersect the graph at 2 points. So this graph is function fx equals x squared minus 4 for x more than equals 0. So this is the domain given in the question. By using algebraic approach, let fx1 equals fx2, the beginning. And then substitute fx1 from fx. We get x1 squared minus 4. And on the right side, fx2 equals x2 squared minus 4. Simplifying this, we have x1 squared equals x2 squared. Therefore, x1 equals plus minus x2. But since x more than equals 0, implies that x1 is equals x2. Therefore, this is a one-to-one function in its domain. So horizontal line test, sketch the graph of x squared minus 4 for the domain. Domain from 0 to positive infinite. Therefore, we can see that the graph is from 0 to positive infinite, and when x0, y equals negative 4. And when we draw a horizontal line, y equals k, the graph cuts the line only at one point. If we draw it here, 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 we also can get only one intersection point of the line and the graph. Therefore, this is the graph of one-to-one function. If f composite gx equals g composite fx and equals x, therefore f is inverse of g. Remember the composite function? If F composite G same as G composite F, and this is equals X, we can conclude that F is inverse of G. Example 2. Find F composite Gx and G composite Fx. How are they related? Let's find F composite Gx. Okay. If Fx equals 3x plus 6, Gx equals 1 over 3x minus 2, Fgx equals F, the input now, 1 over 3x minus 2, which is the Gx function. Okay. Now this is the new input for function F. Therefore, we change the input of function f becomes 3 times 1 over 3x minus 2, which is this the input, okay, plus 6. And simplifying this, we get this is equals x. Now, find G composite f. G fx equals G 3x plus 6 because fx is 3x plus 6. So, 3x plus 6 is the new input for function G. Therefore, we get 1 over 3x plus 6 minus 2 equals x plus 2 minus 2, which is equals x. When F composite G is equals to G composite F, and it is equals to x, we can conclude that F equals G inverse and G also the inverse function of F. Thus, F and G are inverse for each other. For question B, fx equals square root x minus 1 and gx equals square x squared plus 1 for x more than equals 0. Find composite function f composite g. Therefore, gx equals x squared plus 1 now is the input for function f. Therefore, from fx equals square root x minus 1, we get f x squared plus 1 as square root x squared plus 1, the new input, minus 1. This is equal square root x squared. Since x greater than equals 0, we just consider square root x squared equals x only. For g composite fx, this is equals g, the new input, fx, which is square root x minus 1. Therefore, by substituting square root x minus 1 into function g, we get square root x minus 1 square, the new input, plus 1. Simplifying this, we get x minus 1 plus 1, that is equals x. Since f composite g is equals to g composite f, which is equals x, f is the g inverse and g is the f inverse. Inverse function coordinates. If we have function f with coordinates 1, 0, 4, 5, and 6, 9, therefore, the f inverse has coordinates 0, 1, 5, 4, 9, 6, which we interchange the first and second coordinates. As you can see from function f here, domain of f are 1, 4, and 6. The range for 1 is 0. When we plot it on f inverse, we have the coordinate as 0, 1. As for the second coordinates, 4, 5, x is 4 and y is 5. For f inverse, x is 5 and y is 4. For the third coordinates, 6, 9, x is 6 and y is 9. For f inverse, x is 9 and y is 6. Therefore, the domain of f is equal to the range of f inverse. And the range of f is equal to the domain of f inverse. Let's say we have function f 1, 0, 4, 5, 6, 9 and coordinate for f inverse 0, 1, 5, 4, 9, 6. if we do the composite function f inverse for the first domain of f inverse 0, which is this set of coordinate, f inverse 0 is equals 1 and f1 is equals 0. For f composite f inverse 5, f inverse 5 is 4 and f4 is 5. For f composite f inverse 9, f inverse 9 is 6 and f6 is 9. Similarly, if we do f composite f inverse composite with f, for the first pairs, f inverse composite f1, f1 equals 0, f inverse 0 equals 1. F inverse composite f4, f4 is 5 and f inverse 5 is 4. F inverse composite f6, f6 is 9, f inverse 9 is 6. In general, f composite f inverse is equal x and x in the domain of f inverse. And f inverse composite fx is equals x and x is the domain of f. Remember that f does not have an inverse if it is not one-to-one function. Activity 1. Finding the inverse from a graph. The inverse is a reflection in the line y equals x. Step 1. Draw the points and the reflection line. For example, we have 3 points on the graph. And we want to reflect the points on by the reflection line y equals x. If we look at the first point here, the coordinate is 4, 0. Therefore, when we reflecting this point on line y equals x, the image is this point, which the coordinate of this point is 0, 4. For the second point here, the coordinate is 5, -3. If we reflecting this point on the line y equals x, we get the image is this point, which is the coordinate of this point is -3, 5. And for this point with coordinate 0, 1, we reflecting this point on the line y equals x, we get this point, which this point has coordinate 1, 0. We can see a definite graphical relationship between the points of the function and the points of the inverse. Now, Suppose you are given this graph. Draw the reflection line, which is the line y equals x. Eyeball the graph and draw the diagonals from known points on the graph to their reflections on the other side of the line. Like this. As you can see, this part of the graph can be reflected the other side of the line. This part of the graph can be reflected to the other side of the line. Draw the graph. Symmetry property for the graph of f and f inverse. The graph of y equals fx and y equals f inverse are symmetrical with respect to the line y equals x. For example, the graph y equals fx, the line y equals x, and the reflecting graph is equals f inverse function. Find f inverse. From previous, we know that f composite f inverse is equals x. Now, let's say we have fx equals 3x plus 2. Therefore, by using the properties f composite f inverse equals x, we get 3f inverse plus 2 from here. Now, let f inverse x as the subject. Therefore, we get f inverse x is equals x minus 2 over 3. This is how we find the f inverse from the properties f composite f inverse equals x. If we sketch the graph, fx equals 3x plus 2 is this line. And the reflection line y equals x. Therefore, the f inverse is the function x minus 2 over 3. From the graph, we can determine that domain of f inverse is real numbers and range of f inverse is real numbers. Example 1. Find f inverse and its domain and range. Sketch the graph of f and f inverse in the same coordinate system. Question A, fx equals x cubed minus 1. By using f composite f inverse x equals x, we get f inverse x power of 3 minus 1 equals x. Therefore, f inverse x power of 3 equals x plus 1. And we get f inverse x equals cube root of x plus 1. Domain of f inverse is real numbers and range of f inverse is real numbers. The graph of fx is a cubic function like this, and the reflection line y equals x. Therefore, we get the inverse function is this graph. Question B. Fx equals x squared minus 2x plus 2. This is the graph of this function. Therefore, This is not a one-to-one function because by using horizontal line test, we get two intersection points of the horizontal line and the graph. F is not one-to-one function. We must restrict the domain either to 1 to positive infinite, which is this area, or from negative infinite to 1, this area, because the minimum point occurs at 1, 2. Therefore, when we restricted the domain, as this example, x more than equals 1, we get fx equals x minus 1 square minus 1 plus 2, which is we need to completing the square to get xx subject. By using composite function f composite f inverse equals x, we get f inverse x minus 1 square plus 1 equals x. Therefore, f inverse x minus 1 is plus minus square root x minus 1. And f inverse x equals square root x minus 1 plus 1. Why we take the positive values only? Since f inverse x is more than equals 1, therefore f inverse x minus 1 is more than equals 0. That's why we take the positive values only. Now we sketch the graph, which it is half part of the original graph. It is in the domain 1 to positive infinite. And the graph of y equals fx is like this. Draw the reflection line y equals x. And we reflect the graph y equals fx on this line. Therefore, we have y equals f inverse x as this graph. Now, for the case domain x less than equals 1, by using completing the square as a preparation to make x the subject, therefore we get fx equals x minus 1 square plus 1. By applying the concept of composite function f inverse x equals x, we get f inverse x minus 1 from here, square plus 1 is equals x. Now, let f inverse x as the subject. We have f inverse x minus 1 equals plus minus square root x minus 1. To take positive or negative values, we check f inverse x less than equals 1 from here. Therefore, f inverse x minus 1 less than equals 0. Then we take the negative part only. It implies f inverse x minus 1 equals negative square root x minus 1. And f inverse x equals 1 minus square root x minus 1. From the graph, this is the other half part of the original graph, which is the domain is from negative infinite to 1. Draw the reflecting line y equals x, and reflecting the graph, we get the graph of f inverse is like this. Example 2. Determine whether the following function has an inverse. Hence find f inverse and its domain and range. Sketch the graph of f and f inverse in the same coordinate system. Question A. fx equals 3x plus 2. Draw the graph, and by using graphical method, we draw a horizontal line And observe that y equals k cuts the graph at only one point, which the conclusion fx is one-to-one function. Therefore, f inverse x is exists. If we're using algebraic approach, we let fx1 equals fx2. Therefore, 3x1 plus 2 equals 3x2 plus 2. Simplifying this, we get 3x1 equals 3x2 and x1 is equals x2. Since fx1 equals fx2 implies that x1 equals x2, we conclude that fx is one-to-one function which the inverse function is exists. Question B, x squared plus 4x plus 1. The graphical method. From the graph and using horizontal line test, we observe that there are two intersection points of the graph and the line. Therefore, gx is not one-to-one function, and the g inverse does not exist. hx equals square root x minus 2 for the domain x more than equals 2. When x equals 2, we get h2 is 0, and the domain is from 2 to positive infinity, so this is the graph. By using horizontal line test, there is only one intersection point between the graph and the line. Therefore, hx is one-to-one function, and h inverse x is exists. By using algebraic approach, hx1 equals hx2. Therefore, square root x1 minus 2 equals square root x2 minus 2. Squaring both sides, we get x1 minus x2 equals x2 minus 2. Simplifying, we get x1 equals x2. Since hx1 equals hx2 implies x1 equals x2, hx is one-to-one function. Therefore, the h inverse is exists. What is the inverse function? We begin with h composite h inverse x equals x. Now, this is the input for function h. Therefore, square root h inverse x minus 2 equals x. Square both sides to remove the square root on the left side. Therefore, we get h inverse x equals x squared plus 2. The graph of hx is this. By reflecting the graph with the line y equals x, we get the graph of h inverse x is this graph. Domain of h inverse equals with the range of h. Domain of h inverse is from 0 to positive infinity. Therefore, it is the range of hx. And range of h inverse from 2 to positive infinite. Therefore, it is the domain for hx. Next, function negative x squared plus 5 in the domain x more than equals 0. By using graphical method, we draw the graph of this function. When x equals 0, y equals 5. And it is the set graph because a is less than 0. And the graph is like this. Draw the horizontal line. You observe that only one intersection point of the line and the graph. Therefore, Px is one-to-one function and P inverse x exists. Now we want to find the P inverse. When Px equals negative x squared plus 5 in the domain x more than equals 0, by using P composite P inverse x equals x, we get negative P inverse x squared plus 5 equals x. Therefore, we get negative P inverse x squared equals x minus 5 and P inverse x squared equals 5 minus x. Then, by square root both sides, we get P inverse x equals plus minus square root 5 minus x. Since the domain is x more than equals 0, therefore we take the positive part, P inverse x equals square root 5 minus x only. Sketching the graph, this is the graph of Px. When x more than equals 0, when x equals 0, we get y equals 5. And when y equals 0, we get x square root of 5. And actually the graph is continuous like this. And reflecting the graph by using the line y equals x, we get at this point 0, 5, we reflecting it becomes 5, 0. And at this point square root 5, 0, we get 0 square root 5. And actually the graph is continuous like this. Therefore, we can look from domain of P inverse, which is here. It is from negative infinite to 5, and it is also the range of function P. And range of P inverse is domain of P, which is from 0 to positive infinite. We can do some more exercise. Take a final answer from this slide. End of 4.4.